Hello all, I welcome you all to the 13th lecture in this course E690 ATM. Today we will talk about thermodynamics of particles and particularly electrons and bosons. These are important because finally it is this thermodynamics which determines how the electrons are distributed in the available states that are there in a periodic lattice as we saw previously before mid-sem, right? So now we want to change the temperature of the system. Previously we were talking about 0 Kelvin. Now we are going to talk about non-zero Kelvins, non-zero temperatures, and then see how the electrons are distributed in the materials in the given density of states, right? So when we talk about thermodynamics, one has to know that thermodynamics is study of macroscopic world. What we mean is we have infinitely many particles and we can always talk about averages. Infinitely many particles, and what we talk about are only averages. What we mean is we do not care about how individual particles behave, and we are happy to know about an averaged quantity such as energy, velocity, and such. So to begin with such discussions, now let us talk about, let's say, a collection of particles. Right now we are not going to distinguish them between electrons and photons or bosons or such. Let's say we have a collection of particles, a bag of particles, okay, and each of these particles have two important properties. One is the position x and the momentum p, right? According to classical mechanics, the total energy of the particle is determined by the momentum p, which gives you the kinetic energy, and the position x, which gives you what is the potential energy that the particle will have at any such position. If you know the position and the velocity and the momentum, you know everything to know about that particle, right? So when we talk about position and the momentum of individual particles, energies of individual particles, we call it a microscopic state or microstate. And when we talk about a collection of such particles, we call it a macro state or macroscopic state, right? Because once we start talking about collections, then we start to talk about averages and such. So let's say that we have one particle. Each particle, let's say, can have energies in epsilon 1, so on till epsilon infinity, right? So this is just to tell you that a particle is almost free and it can take any velocities that it wants, and it can move in some potential profile, so it can take any total energy that it can have. And all particles are similar, are identical. Right. The one important assumption that we have here is the probability for any individual particle to take energy epsilon I is constant. So what we mean is any particle in this collection, the probability for that particle to have an energy epsilon I is going to be the same. You cannot distinguish between each one of them. Each one of them have the same mass, looks the same, moves in the same averaged velocity, right? And the probability for it to take any particular energy value remains the same. That is what finally tells you that all of them are indistinguishable. So this is one important point at which thermodynamics starts, particularly in the statistical thermodynamics that we're talking about, right? So once this is given, now let's start doing some collective things. Okay, so if we take a bag of such particles, and let's say if the bag of particles is isolated, that means it does not share energy, it does not distribute particles between each other with this and the environment, this is isolated, the total energy E total is summation of all the epsilons of these particles at any point in space, and this total energy is invariant at thermal equilibrium. What we mean is, I take each of these particles and summate its energies that it has at any time, right? So basically it can take some random energies, but at any time I summate all the energies, I get what is called total energy, and this total energy does not vary at thermal equilibrium. We are always talking about thermal equilibrium, thermodynamics. At this equilibrium situation, we assume that the total energy is invariant. Once this is given, let us take a collection of particles, say SA, right? So basically we have this, I draw a line and call the left hand side as A and the right hand side as B. If this is so, and if the total energy on the left is EA, the number of ways the left can have energy EA is called as the multiplicity of that. So what we mean is, I have a collection of particles to the left hand side of this line. Each of them can take some random energy values, but all I know is the summation of these energy values is EA, right? So what it means, there are different ways this particle can distribute itself to have a total summation of EA, and that different ways in which I can put them together is gamma, or is omega A. The same thing, the number of ways the right hand side can have energy EB is omega B, right? So this is just, I'm dividing this entire set of particles into two. Whatever is, let's say I take a small bunch of particles whose summation comes out to be EA, whatever their value is, some random value, and the rest I call it B, right? If this is given and I know that D E total equal to 0, and E total has to be summation of both the energies, right? So D E total is DEA plus DEB equal to 0. So what I mean is, any change in the total energy of this A will adversely affect the total energy of B, right? Because we say the total energy is conserved. If I just move this guy a little bit away, its total energy will increase, but that will overall decrease the total energy in B, right? And the total multiplicity omega will be a product of multiplicity of A into the product of multiplicity of B. Why? So let's say for one configuration of these particles, let's say on the B side, which gives you energy EB, there are omega EA ways to arrange the particles in A, right? So for each omega A, omega B, you have omega EA times ways of arranging it to have energy EA and EB, right? So the total ways in which you can arrange both of these things to have total energy E total will be a multiplication of this one, right? Now once again we do this differential, and this will turn out to be d omega A omega B plus omega A d omega B. If I divide one by the other, I get d omega by omega equal to d omega A by omega A plus d omega B by omega B. And given this particular condition, at thermal equilibrium, this has to be 0. So what we get is d omega A partial dEA plus d omega B by dEB, right? This is partial, of course, will turn out to be 0. And of course, dA and dEB are related to equal and opposite, which tells you, right, dou omega A by dou EA should be equal to dou omega B by dou EB. This is an important consequence under thermal equilibrium. If we have a bunch of particles which are divided as A and B at thermal equilibrium, any change in energy A will have, basically I have missed a sentence here. So this equation can obviously be written as d ln of omega equal to d ln of omega A plus d ln of omega B. So this is d ln of omega A, d ln of omega B, right? This is dou ln of omega A, dou ln of omega B, right? So all we're trying to say is, for any small change in the energy of A that we want to segregate these two, they are equally matched with changes in the ways of multiplicity of omega B, right? Well, this fundamental equation is of tremendous importance. What we will proceed now is what will be more relevant to us. So now we will go and see how each of these particles are distributed in terms of the probability of finding the energies of these particles, and so on and so forth, right? So once again, let us look at a big collection, and there are big collection of particles. These particles have random velocities and random energies, right? So it can have epsilon i's ranging from 1 to infinity, so they are all random. If I take a small collection of particles, right? So there are many such particles. If I take a small collection of particles and ask this question, what is the probability of the small collection of particles to have energy EI? Let's say I take n particles, okay, some capital N out of the bag. The bag has some infinite number of particles, really large number of particles. From there, I take a small collection, a handful, let's say n equal to 10, right? I take a handful of particles and ask this question, what is the probability for summation of energies of this handful of particles to have an energy EI, right? So what is this value? So this is given by this expression, P of EI, probability of n particles to have energy EI is given by 1 by z e power minus beta EI. So we can actually derive this from this particular equation that we came up with, but because of the need to reduce the mathematical rigor, I don't go into this derivation and give you this result. Anybody who's interested, please always contact me, and I can actually derive in a very few number of steps this particular equation, which according to Feynman is the pinnacle of thermodynamics, and anything that you work in thermodynamics follows from this particular equation. So this is called as the most important equation in thermodynamics, and this Z is called as the partition function. you can already see the presence of this Boltzmann term e power minus beta ei. Ei is the energy, the probability of the energy that you are looking for, right? So let me repeat. We take a collection of n particles, and if the question is what is the probability that the collection of n particles have a total energy ei, is given by 1 by z e power minus bi. Obviously this 1 by z is a normalization factor, and this is written as z is summation of all possible total energies ej, right, e power minus beta ej, right? So this is very simple. So what it means is this summation should actually, this product should eventually give you 1, right? So if I summate what is the probability of this the probability of this n particles to have energies, the summation of all such probabilities should eventually give you 1, right? So basically, and hence it is normalized by summation of all possible energy sums that you can have in this n particle subset that we took, right? So this is called as the partition function z, and this is the probability to have for an n particle collection to have energy ei, right? With this, let's say we take let's say logarithm on both sides. Log z is, of course, so okay, so maybe I missed a small thing here. Beta is called the inverse temperature, and beta is equal to 1 by kBT. Kb is the Boltzmann constant, T is the temperature. There is something that I would like to mention here before we proceed to see the thermodynamic potential energy and so on and so forth. The temperature T is set by the region outside this boundary, this bag of n particles that we took. This T sets how many states you can have outside this bag, and this e power minus this ei is just an is a property of this bag of n particles, right? So this particular equation couples the environment or the heat bath with the system. So this bag of n particles is called as the system, and the heat bath, that is the particles outside of this bag which dictates the temperature of this particular system, is called as the heat bath. Okay, and this particular arrangement is called as a canonical ensemble. Let's not go into that detail, but it is just for you to know. When you are reading further information, you will know what we're talking about. So from here, let us define a term F, which is called the Helmholtz free energy or thermodynamic potential energy, which is defined as minus ln z by beta, or it is minus kBT ln z. Why we use this is you can easily see that now you can actually write this P of n particle of energy having ei is written as e power minus beta ei minus f, right? So because 1 by z is basically e power beta f, so you can replace the previous expression to be something like this, and f is called as thermodynamic potential energy or Helmholtz free energy. Okay, one can calculate, given that you have something like this, what is the average energy of such n particles that I can take, right? So basically what we mean is, if I take these n particles, there is a probability of these n particles to have different energies, which is given by this expression. Now that this is given, what is the average energy given or taken n particle in random? What is the expectation of this energy, right? If I ask that question, which is given as average energy of n particles. U, or expectation value of energy, is given by summation EI PI, right? This is of n particles, of course. You don't need I here. And this can be calculated pretty easily, which will be summation of EI e power minus EI by kBT divided by e power minus EI by kBT. This is Z, right? And obviously this can be written as minus 1 by Z dou Z by dou beta. Beta is 1 by kBT, right? And this is basically 1 by Z dou Z is basically dou by dou beta ln of Z. Z is the partition function. So the average energy is given by 1 dou by dou beta ln of Z. So this is another important thermodynamic equation which gives you that once you know the partition function, you can tell what will be the average energy of an n particle collection that you have. As I told previously, Z is basically an integral property of the n particle system, and beta, or the temperature, is a property of the heat bath. So both the heat bath and the system determines what is the average energy of this system. Okay, so let's, at this point, let me reiterate. Till now we are talking about a collection of n particles, and each of the particle in the collection can take continuous values of energy. Though we have labeled it EI to E infinity, this is infinitely large set of energies, and it is all continuous, and we have been treating all these things in the classical limit. But of course, when we are talking about electrons in periodic lattice and such, we know that the energies are not continuous. In the quantum regime. And the second thing is occupation of a particle in an energy, at least in the classical limit, do not affect the occupancy of the particle, of other particles in the same energy. And this is something that we are going to change now, right? Because now that we have defined the partition function, we are in a place to describe the distribution of electrons and quantum particles in a material. So we are going to deviate slightly from this particular description in the classical limit. So we are going to include what is called as Pauli's exclusion, which tells you no two fermions can have the same quantum numbers. If the energy is determined by n, L, and m, it is the spin values which will differ, and there can be only two possible spin values for a fermion. So only two electrons can have the same energy, right? This is the Pauli's exclusion principle if there are fermions. If there are bosons, so now we are differentiating between the particles, right? Now we already have differentiated between fermions and bosons. If there are bosons, there is no such limitation. Why? I suppose you must have known about the the reasons why you have two kinds of particles, fermions and bosons, right? It all comes from the fact that the particles that we took are indistinguishable. What do we mean? That the wave function psi of, let's say we are taking two particles, psi of r1 and r2, particle 1 that is psi 1 in r1 and the second particle in r2 is the same as r2 comma r1. So psi is a collective wave function of two particles r1 and r2. So what we mean is, let's say we have a particle, let's say we have a red particle in r1 which has this particular shape, and let's say we have a green particle in r2 with this particular shape, and if these two are indistinguishable, if we have, let's say in r1 we have the green particle and in r2 we have, let's say, the red particle, if these two are indistinguishable, any measurement that I do on the collection of these two particles should give me the same answer. Now there are two ways in which this indistinguishability can be established, right? The first one is psi 1 r1 psi 2 r2 plus psi 1 r2 psi 2 r1. The other one is psi 1 r1 psi 2 r2 minus psi 2 r1 psi 1 r2, right? If I have this, so there are two ways to write it. The second one, in which the wave function actually flips sign when we interchange the particle, is called as a fermion. The first one, in which the wave function do not interchange, we call it the bosons. Why? If two particles are exactly the same, right, and if it has the same energy, the wave functions looks exactly the same. If you see that if I do this expansion, this psi will turn out to be 0 for fermions. If all the four quantum numbers which describe these two functions are the same, the wave function when we interchange these two particles will become 0. So we lose the indistinguishability if we have two particles which have the same quantum numbers. Whereas for bosons, because we have a plus sign between these two terms, indistinguishability does not ensure that the two particles should have different quantum numbers or different energies, right? It is this reason why fermions cannot have the same quantum numbers, cannot have the same energies, right? Now that this particular aspect is done, let us go further and then take a look at individual energies in the collection of these particles, right? So now let's once again talk about this huge collection of particles. Now these particles, let us say, are for our concern just electrons. There are huge number, infinitely many such particles, and out of this infinitely many such particles, I take only a small collection which has, let's say, n particles, n number of particles in this collection. Now I ask, what is the probability? Of course, because each of these particles are electrons, for each particle there are distinct energy levels, right? So this is epsilons, E1 to Em. There are distinct energy levels. Now I ask this question, for each electron, what is the probability that this energy level is filled? This, let's say, some energy level I. Probability that energy level EI is filled for n electron collection. Probability that the energy level EI is filled for a n electron collection. Why does this make sense? Because if there are quantum particles, we showed that the energy values are discrete, and if they are fermions, no two electrons can occupy the same energy level, right? So that occupancy problem, let's say if this electron, we call it A, occupied E1 or epsilon 1, this will forbid the second electron B to occupy the same energy level, right? So all our previous descriptions have to be slightly modified. But let us now continue and ask this question: what is the probability that that energy level EI is filled in an n electron collection, right? So this f of I for n electron collection can be written as a summation of all such probabilities such that that energy level is filled, right? So basically what I'm saying is I take a summation of all total energies Ej. So I can get the energies Ej by several combinations of these particles, a summation of all such combinations where Ei is filled. Okay, so this gives me the probability that that energy level Ei is filled, right? So basically, if I reiterate, what I'm trying to tell is the probability that this Ei is filled is summation of all the possible combinations giving you total energies Ej, in which the energy state Ei is filled, right? I suppose it is clear. Now this I can write in another way. It is 1 minus summation of all such collections with probabilities of energies Ej, in which the energy Ei is unfilled. So here I have a collection probability of an n electron collection of energies Ej's, right? The total energy Ej, such that Ei is unfilled. I mean, taking all such collections and adding all the probabilities. Now this can be written as 1 minus summation of all the j states, such that now I take an n plus 1th electron collection. So I have an n electron collection here. I add another electron to this collection such that Ej minus Ei, right? Such that Ei is now filled. So I take an n plus 1 collection such that the state Ei is filled and subtract the energy Ei. So this summation will give me the probability that Ei was unfilled, and 1 minus that will give me the probability that Ei was filled. Why I go through this roundabout way of proving this is because I know how to handle this particular expression, right? So what is P of n plus 1 Ej minus Ei? Remember, Ej is any such energy level here, and Ei is one particular energy level where we want to find the probability. This is obviously given from our previous treatment, e power minus beta Ej minus Fn minus Ei, right? Fn is the partition function for n electron configuration. Because it is Ej minus Ei, you have only Fn, right? If I introduce a new variable mu such that it can be written as f of n plus 1 minus f of n. Remember, f is the thermodynamic potential energy we spoke before. It's a function of the partition function with n plus 1 particle, and the partition function, logarithm of partition function with just n particle, right? If this can be introduced, we can actually reduce this particular expression as e power minus beta mu minus Ei into p power n plus 1 Ej, right? P power n plus 1 is the probability for a n plus 1 particle collection to have an energy Ej. Now if I substitute that back to our previous expression, the probability for an energy level EI to be occupied for an n electron configuration is given by 1 minus e power EI minus mu into beta summation of Pn plus 1 Ej. Remember, Pn plus 1 Ej is given by this one, right? So basically it is a probability that the ith state is occupied in an n electron collection. This will be 1 minus e power beta EI minus mu f I n plus 1, right? In an n plus 1th collection, what is the probability that the energy EI is occupied? Obviously, if n is extraordinarily large, the probability that EI is going to be occupied is not going to change between n and n plus 1 largely, right? So basically we are going to say this value is very similar to Fi of n. If that is given, then Fi of n can be written as 1 by 1 plus e power beta EI minus mu. And this, my friends, is the Fermi-Dirac distribution. Right? So we have taken the partition function and we have used the fact that you can have only one electron in one particular energy in this particular way, where we have written the probability that a state is occupied is just 1 minus the probability that that state is unoccupied, right? Because there cannot be n electrons in the same energy level. Because you have used Pauli's exclusion principle here, you can actually reduce this further. And the fact that we cannot actually calculate this particular conditional probabilities, we use a small sort of a trick where we say that we use conditional probability when we are talking about n plus 1th state, and then we assume n plus 1 and n does not largely change, and we come up with the derivation for the Fermi-Dirac distribution. Right? So at this point we will stop, and the next time we meet, let us proceed further later. Thank you.